Here's another simple class example of conservation of energy and how work can interfere with the conservation of energy, I guess, in this case. So the question is, the force of the car's engine that's exerted for 4,500 newtons only acts for 10 meters of the trip. What is the final velocity of the car? All right, so I can see the car is 1,000 kilograms, and I can see on the lower left, that it's moving at 3 meters per second from left to right, and I can see that the work is only done across 10 meters of the distance. The rest of the time, the car is just going to coast along the whole trip, and it's going to end up being 3 meters higher than where it started. So the first thing I need to figure out is I've got this non-conservative force of the work of the engine. Non-conservative meaning I'm not going to get this energy back. It's not a potential energy. That's the 4,500 times 10 newtons, 10 meters. So I need some way to figure out if it's going to add energy to the initial energy, or if it's going to remove energy from the initial energy. So what I'll start with is looking at the 4,500. I'll take one hand and point in the direction of the force. With my other hand, I'll point in the direction of the displacement. Since my two fingers point in the same direction, that's going to tell me that energy is added to the initial energy of the car. So I'm going to start with sum of the total energy at the bottom plus the work of the engine equals sum of the total energy at the top. And that's because my displacement and my force go in the same direction. And when I'm thinking about work, it's going to be that 4,500 times the 10 meters. That's all I need to be concerned about for the actual work. So not the whole distance, just that part of it. All right, so now it's going to total energy at the bottom, that's kinetic and potential, plus the work of the engine equals kinetic and potential energy. Then I go through my series of questions, or the LOL energy graphs. The kinetic energy on the left-hand side, I should ask, is it moving? And it is. So I'm going to keep that kinetic energy. Is it above the other location's height? It is not. So that's going to go away. No potential energy stored in the gravity. The work of the engine I'm going to leave alone. Again, that's positive because the force and the displacement go the same direction. And the kinetic energy and potential energy on the right hand side, let's figure those out. So at the top, is it moving? I think so, so I'm going to keep that. And is it above the other location's height at the top? Well, it's the top, it's the higher of the two, so the answer is yes, it's higher. So I'm going to keep that energy. So now I put in my equations that I need. So that's going to give me, let's see here, 1 half mv squared plus force times distance for the work equals 1 half mv squared plus mgh. And then when I do my numbers and units, 1 half 1,000 kilograms times 3 meters per second squared plus 4,500 newtons times 10 meters plus 1 half 1,000 kilograms times v squared equals 1,000 times 9.8 meters per second squared times 3 meters. Notice the 10 meters is just the distance that the work was done. And then I'll solve this for the velocity. And when I do that, I get 6.34 meters per second to 3 sig figs.